So my name is Yoon Ho Kim. I'm from University of Science and Technology, or PostPad as we call. So I would like to talk about a very simple multi-photon interference experiment. So over the last 2 days, it has been actually quite interesting for me, especially because I was able to see many of the recent work by really powerful groups. And in some sense, it was a little bit overwhelming to me because everybody's using all this fancy technology. Right? So we've been seeing quantum walks using photonic quantum circuits made on silica, and a lot of integrated photonic chips, which is actually quite interesting, and also boson sampling. And then we heard for the last 2 days a lot about permanent, and I really have to confess that in like Downey, I never heard about permanent until the papers came out. And I thought maybe there's some sort of a conspiracy in quantum optics that what's permanent? I never heard about it. That suddenly everybody knows. So
actually, it was Jeff Kimball who had never heard about the permanent. I had heard about it.
So
but you're a good company.
I really have to teach myself what that is really. And then especially yesterday, Vincenzo told in his talk that the fundamental dB is because permanent is 0. I mean, okay, but that's not how we learned in quantum optics. So I guess things are really shifting. And then even yesterday, someone actually turned into the dark side. So there was quite a lot of development. And but I guess what I will want to do is to tell you about a very simple experiment. It's a single beam splitter, basically. It's a very inexpensive single beam splitter. And then we want to interfere a wave packet. It can be a single photon wave packet. It can be biphoton wave packet, or it can be like a wave packet having more than 3 or 4 photons. So in that sense, it's a multi-photon interference experiment. So in particular, I want to talk to you about 2 experiments that we have done some time ago. So first, so we'll talk about a quantum to classical transition experiment where the transition turns out to be non-monotonic when you go from quantum regime to the classical regime. Then I'll also talk to you about a multi-photon interference experiment where the coherence time, as you define from an interferometry measurement, turns out to be really dependent on how you measure it. So let's talk about the first one. But before, these are the people who have actually done the work. As I was preparing the talk, I was really sort of shocked. I mean, I knew it, but shocked in the sense that myself and Andreas, I mean, we collaborated, and we are the only 2 ones who are still at the same original institution. All the other people have left, and really tells me I'm getting old, and I guess most of you are getting old as well. So, yeah, especially you.
Okay.
So let me talk to you about the non-monotonic quantum.
I think you'll someday catch up.
Yeah, I know. So I'm going to start with this cartoon that probably a lot of you have seen it. It's by Drake. It's published in this magazine called Southern Science. So in this, according to this cartoon, you have the quantum domain, right? And then you have the classical domain. And then the rules of the quantum domain is that you interfere, particles interfere. And in the classical domain, there's interference, but the waves interfere, right? So from the quantum domain to the classical domain, you transit, and this happens because of decoherence. So there must be some sort of a quantum to classical transition because the line may not be that sharp. And what you notice here is that in this cartoon, in the horizontal axis, you see it's a really number of the atoms, so the size of the quantum system, but now we know that it doesn't really have to be the size of the system.
You know who the guy with the hat is?
Do I have to know?
It's Bohr. You could tell by the eyebrows.
Yeah, but I've never seen him in person, so.
Me neither.
Just by photo. So in the quantum domain, your particles do exhibit interference. So one of the classic experiments there is that basically you take a double slit and then you shoot your particles and then you see whether there's interference. And people have done this sort of experiment for quite many times. So with the photons and with the electrons and with even fuller rays, you can actually observe this kind of interference fringes. So what's quantum to classical transition in these cases? So in quantum case, your particle, it does exhibit interference. So on the screen, you will see a very high visibility modulation of interference fringes. And it happens because the path, let's say this particle going through this path or this particle going through that path, they are indistinguishable. Although yesterday we heard a very interesting talk where this path actually can be more complex, but let's rule that out for now because it appears that the effect is very small. So for now, let's ignore it. So this is the quantum case, and what's the classical case? There's no interference. So this path and this path, or this probability amplitude, they are completely distinguishable. So there's no interference. So what you see is sort of actually you will see a 2K here. But so you have now that we have defined the quantum domain and the classical domain in the particle case. So what about transition, right? So transition is that you basically lose the visibility gradually. So if you start from the quantum case and then somehow you end up with the classical case, if these two paths are completely indistinguishable. But it's also possible that these two paths are less than perfectly indistinguishable, so that you lose the visibility sort of slightly. So if these two paths are slightly more distinguishable, and then you will have less interference visibility. And then if it's slightly more, the visibility will get reduced, and then eventually you will have nothing. So in this sense, you go from the quantum interference case, that's basically particles to interfere, and then you go to classical case. So if I plot the visibility as a function of, let's say, decoherence, I normalize decoherence from 0 to 1. And you will have sort of a monotonic decay. I mean, it doesn't have to be this particular form, but you can see that this sort of a decay, or the visibility decay is going to be monotonic. So this is actually what I'm going to talk about. So this is in the case of a single photon interference, or a single particle interference. So you have a monotonic quantum to classical transition. Let's see what happens when you have two particles. So you can define quantum case and classical cases very easily, right? So when you have a quantum case, these two photons or two particles, they interfere. For that to interfere, this interference to occur, these two particles must be completely indistinguishable. So whenever that happens, in the case of photons, the joint detection probability of finding a photon here and then finding another photon here equals to 0. And I say that, or in quantum optics, a lot of people have studied for a while, and then we all kind of attribute this effect to this quantum interference, where this photon simply transmit, or this photon transmit, and also this photon gets reflected, and this photon gets reflected, and these two probability amplitudes, they are off phase, and then they interfere. Of course, you can probably say this is due to the permanent being 0, but I guess for me it's more pictorial, easy to understand. And the classical case will be that these two particles will be completely distinguishable, so that you do not have any interference. And in that case, these two detectors firing jointly, there is non-zero probability. So these two, it just happens randomly, so there will be always some background event. And what about the transition, right? You can actually create this kind of transition. You can make this by making these two photons completely indistinguishable and then completely distinguishable. And you can use polarization, but in this case, you can actually try to use the delay between these two photons. So when the delay between these two photons are much longer than their coherence times, and the arrival time at these two photons at the beam splitter, they are random, and then they do not interfere, so this corresponds to our classical case. So in the quantum case, these two photons arrive simultaneously, so you have a zero coincidence count. And in the classical case, where the delay between these two photons arriving at the beam splitter is much longer, bigger than the coherence times, and then you have this random detection event. So if you do an experiment like this, we have a plot that's very familiar to us. So basically, you go from the quantum case where the coincidence count is completely 0, and then you go to a classical case where you have a background count. So this is known as the homo-Menzel interference. And I guess most of us in Asia are somehow very proud that many of this earlier work was done by fellow countrymen, or for instance Chinese, Hong, for instance Korean. So what about 4-photon interference, right? So I'm sort of following the classic experiments that have been already published. So in this case, you have a photon wave packet having 2 photons in each, and then they interfere at a beam splitter. So they meet at the beam splitter, and what you're looking at is that the probability of finding 4 photons at this output port C. So in the quantum case, where these 2 wave packets completely overlap, the probability of finding these 4 photons at this point turns out to be 3/8. It's relatively easy to calculate. It's having just the 1 beam splitter, right? So, but if you delay this much longer than the coherence time, it happens that the probability that you find a 4 photon at this particular detector drops down to 1/16. So basically, there's about 6 times the difference. And in fact, Oh, Lee, and Wang have done this experiment a long time ago already. So basically, when you have a quantum case, you have a peak in the coincidence count, a 4-photon coincidence count, and then as you move away from the quantum case to the classical case, the coincidence count drops, and then there's this difference in the count rate, which is clearly visible. So in these, I guess, examples, what we see is that, I mean, we have seen sort of a monotonic transition from quantum case to classical case. And we ask ourselves whether this sort of a monotonic feature is sort of universal. So instead of really focusing on the size of the system, or to go from quantum domain to classical domain, if you vary the decoherence, right, you can actually move from the quantum domain to classical domain, and then we can try to exploit and study whether this kind of transition is universal or there are some sort of other features involved. So to study that, I think it's better to have a very pictorial mathematical scheme so that physicists can understand. So what we do here is basically we use a sort of mathematical approach, Graham-Schmidt orthonormalization. That, let's say you have 2 overlapping wave packets. It's a partially overlapping, right? So let's say you have an overlapping wave packet alpha and wave packet beta. They are not coherent states, just the alpha and beta. So this alpha wave packet can be written as a vacuum, and then you apply the creation operator for that particular wave packet. And if it's a single photon wave packet, we just apply, let's say, A1 dagger. And for the other one, you see that there's a sort of partially overlapping amplitude. So this will be, in some sense, interfering with that one. So there will be sort of a indistinguishable part, but there is also distinguishable part. And it's in superposition. So this beta wave packet is basically a single photon wave packet, but it's having 2 components. One that's distinguishable, one that is indistinguishable. And these 2, A2 and A1, are representing distinguishable and indistinguishable part. They're obviously orthogonal. So once you sort of define it this way, you can color code it, and you can try to understand this by using these pictures. So by simply saying, let's say A1 dagger to be, let's say, applied to the vacuum to be a red photon, and A2 dagger applied to the vacuum as a blue photon. And these red and blue photons are orthogonal. And this alpha wave packet is simply red photon, and this beta wave packet is sort of a superposition of red and blue. So now let's apply this to a single photon, or a 2-photon interference experiment where 2 single photon wave packets overlap at a beam splitter. So relatively easily, we see that you have a 2 red photon, and then 1 red and blue, and these 2 are somehow contributing to the coincidence count. So you have an indistinguishable amplitude that is represented here. So basically, you are having 2 indistinguishable photons coming into your setup. And here, you have distinguishable photons coming into your interference part. So these 2 basically contribute to the final outcome. For the final outcome, so basically, we don't really care about how the state evolves. What we care about is what will be our sort of a detection rate, and what will be the shape of this detection rate. So these 2 contribute each independently. And the amount of contribution obviously can be quantified by the C1 and C2. And this C1 and C2 is going to be a function of the delay x. So the indistinguishable part, this weighting factor basically is C1 square, and distinguishable part, the weighting factor is going to be C2 square. And if you plot this, so this is basically it's a function of path length difference. When x is 0, you only have a distinguishable component here, and when you have basically this is basically your quantum case. And in this case, you have a distinguishable component, which is your classical component. It's 0, and as you move away from it, the quantum part decays and the classical part increases, and that's how you have sort of a Hom mental dip. So contribution of these two terms will give you a Hom mental dip. And when you actually try to calculate the probability transition, not only that you have to worry about the weighting factor, you also need to worry about the detection probability for each particular distinguishability type. So, for instance, when you have a completely indistinguishable case, depending on how you detect, I mean, the probability will differ. So, for instance, if you detect one photon here and one photon here, and that probability in the case of an indistinguishable case, you will have 0 probability. But if you try to detect 2 photons here and 0 photon here, that is a one half probability. And if you go now to distinguishable case, the probability changes. So you need to sort of factor this in when you calculate the transition probability. And once you do that, this is what you get. So basically, 1-1 detection is basically you are detecting one photon here, and as you change this delay, you basically have this nice momental dip. And if you detect 2 photons here, and you will basically have some background count, and then you go to a peak in the quantum case, and then you go back to the sort of a classical random contribution case. And in all cases, these are monotonic. And now let's apply this to a 4-photon interference experiment. And things are pretty much similar, except that there's one more term that's coming in. So basically now you have a 4-photon interference experiment. So you have 2 photons here, 2 photons here, and if you sort of write it in a very similar fashion, what you end up is basically you have 3 terms that's contributing to your final detection event. So you have completely indistinguishable case, so all the 4 photons are indistinguishable. And then you now have this term where the 2, they are the same, but the other 2, they are distinguishable. So this will basically give you some sort of background depending on how much weighting factor it has. And then you also have an intermediate term. So out of all 4 photons, only one of them is distinguishable. So these 3 terms will contribute each differently to the final detection event. The weighting factors are obviously calculated by just looking at the coefficients of each amplitude. And if you do calculate this, assuming, let's say, Gaussian wave factor for the Gaussian spectral distribution of the single photons, and this A part, the indistinguishable part, you see that in the quantum case it's dominant. It's always, you only have an indistinguishable case, and then if you move away from the quantum case to the classical domain, it's a sort of a monotonic decay. And the distinguishable component, it rises from having 0 value to a certain value, especially when you go to completely classical case, you only have this case. But then also this term contributes, it's like this. And this is going to give you a sort of a strange behavior when you do a particular detection. So now let's look at the detection probability for each of these different distinguishability types. So when you have a completely indistinguishable case, detecting 4 photons here and 0 photons here, this will be your probability of detection. And now if you change your detection scheme to detect 2 photons here and 2 photons here, there are different probabilities involved. And the same is true for all the other cases. And if you go to now distinguishable case, this number changes. And then if you go to intermediate, also this number changes a little bit. So if you factor this in and then you calculate the total transition probability, I mean the detection probability as a function of x. So this is actually what you get. So as you have seen in the O, Ri, and Wang's paper in 1999, so detecting 4 photons here and 0 photons here will give you a nice, smooth, monotonic feature. But if you try to detect now 2 photons here and 2 photons here, from the complete quantum case to the classical case, you have sort of a slightly different distribution, I mean the transition probability. So this particular case, it becomes monotonic, I mean not monotonic. So in experiment, actually we set out to see this in experiment, and this actually is not a huge difference. So it took a while to actually get this done. So the experimental setup is something that's very familiar to people in this crowd. So I'll skip this part. And but obviously you have a quantum light generation part, and then this interferometry part. And these detectors, we don't have a photon number resolving detector, so we cascade the detectors to detect, let's say, photons number higher than 2. So down conversion, I guess we don't need to talk about this. So in the case of multi-photon detection, 2-photon detection is just the 2 detectors sort of connected by a fiber beam splitter, 3-photon detectors this way, and 4-photon detectors this way. And then these detectors can go here and there and so on. So 2-photon interference experiment, right? I mean, this is a very well-known experiment, obviously. So when you do detect 1 photons, you do see a very nice homomental dip. And then if you do detect 2 photons, you see a peak. And it's well known. So from here, you see, you go from quantum to classical case. It's a nice monotonic transition. And then if you do a 4-photon interference experiment, so basically it's a repetition of O.R.E. and Wang's paper. So basically you go from quantum case to the classical case, and it's a nice monotonic decay. And you measure 4 photons here and 0 photons here. But if you detect 2 photons here and 2 photons here, basically, and then you observe coincidence. And basically you have this sort of a dip here that doesn't appear exactly at the center. So you have sort of a non-monotonic transition from the complete quantum case to the complete classical case. So what about even higher photon numbers, right? I mean, you should be able to do a 6-photon interference experiment, and you are here with 8 photons. It turns out, at least at that point in, I guess, in my lab, we didn't have enough power in the laser, so we couldn't actually do this high photon number experiment. So instead, we did the simulations. So if you go to 6-photon interference, so each wave packet having 3 photons, and if you write up all the possible contributing factors, so you have a completely indistinguishable amplitude. That is, all the 6 photons are completely indistinguishable. And then in the classical case, 3 are same, and then the other 3, they are distinguishable. And then there are 2 of these intermediate terms. So out of 6, you have 1 that's distinguishable, and then here out of 6, you have 2 that's distinguishable. And each of these, they contribute slightly different form of transition from the quantum case to the classical case. So if you calculate the transition probability, basically what you're calculating is the joint detection probability depending on how you detect it, whether you detect 6 photons here or 5 here and 1 here and so on. And if you vary this and then calculate the transition probability or the coincidence modulation, and from 0 to whatever number that you're moving away. And for instance, if you do 3-3 detection, 3-photon detector here, 3-photon detector here, it's a sort of a nice dip. It's very similar to homomental dip. And if you do a 6-photon detection here and 0 here, and also very similar to O.R.E. and Wang's paper, you have a peak here. But if you move away from that, you have a sort of a non-monotonic transition. So it turns out that these non-monotonic transitions appear actually quite more abundantly than just the very monotonic cases. So the 4 cases will be like this, and this is observed in the experiment. And if you go to 6 and 5-1 detection, for 2 detection will give you a really different probability transition. And if you go to 8-photon detection, and these different detection schemes will give you really different modulation patterns. So when you go from quantum case to classical case, and things really do sort of a change very strangely. So I guess what I want to say here for this particular experiment is that as you move away from the quantum domain to the classical domain, these transitions are not necessarily completely monotonic, and then you can explore this in a multi-photon interference experiment. Without using all these fancy, expensive, and I would like to have type devices, but just having a simple beam splitter. So the next experiment that I want to talk about, it's sort of related, and basically involves a different detection scheme that, depending on how you detect, the coherence times that you define, it actually changes. So the schematic is very similar as before. So you basically have photon wave packets that's coming in, and then these wave packets contain different number of photons, and then you interfere them in a beam splitter, and then you measure them differently. So interference obviously occurs when you bring your two mutually coherent beams, right? For instance, laser beams or BC, and they just appear. So classical coherence, I guess, sort of you can say that this is due to interference of waves. And the first instance that this has been reported is obviously by Thomas Young in this very old paper in 1804. Science is that it's a 200-year-old paper, and then I can actually read it. But in Asia, if you think about 200-year-old something, and it's almost unreadable because it's written in Chinese, and even you guys can read it because it's traditional Chinese. So in this particular experiment, what they have done, what he had done is that basically instead of actually double slit, right, he took a very thin slip of card and divided this sun beam into two, and then he let these two beams overlap and then observe interference. Quantum coherence is basically interference of particles then. So how do we then define coherence, right? I mean, it's something that we know very well if you have done optics experiment. So basically you take a pulse, optical pulse, and you delay one with respect to the other, having split it in the beam splitter, and then you recombine them, and then you record the intensity as a function of the delay, and then that's what gives you the coherence time. And this measurement, and if you determine the width, that is your coherence length, or coherence time. But according to the Wiener-Hintschen theorem, we know for a fact that there's a bit more to it, right? So basically the spectral density and the autocorrelation function is Fourier transform. So if you have a wide band light, you have a short coherence length. And this necessarily is different when you go to a pulse regime. So if you have a CW waveform having certain bandwidth, right? And if you detect, if you do an interferometry like this, and then what you see is the coherence time of something, but that's not really equivalent to measuring pulse width of an optical pulse. So just clarify that we are not actually trying to measure width of an optical pulse, whether we are trying to measure the coherence time alone. So let me just skip this part. So then how do I define the coherence time of a quantum system? For instance, a single photon, multi-photon, and so on. Then this obviously we have to rely on certain interferometry, right? I mean, we cannot just give some inherent property of coherence time to let's say a photon. We have to define it. From the measurement, we have to really measure the coherence time. So we need a quantum interferometry. We need to have some sort of interference experiment. This quantum interference can, for instance, in case of photons, it can be a beam splitter. If you go to, let's say, some other test stands, it may be something different. And depending on how you interfere, you may observe oscillatory signal. For instance, if you have a single photon Mach-Zehnder interference experiment, what you get is a very oscillatory signal, but the actual coherence length or coherence time is the width of this signal, right? So you don't really care about these fine oscillations at that point. But you may also have a non-oscillatory signal. For instance, in the case of a Homo-Mendel dip experiment, you don't actually have oscillations, you just simply have a dip or a peak. And some other experiment, you also have a dip or peak. And this peak, I mean, the width of this dip corresponds to the coherence length of a system that you are interfering. So these experiments, obviously, the first one having been the Homo-Mendel interference experiment, and there are other interference experiments, for instance, electrons and so on. But we will be focusing on photons in this case. So if you do a single photon interference experiment, right, it's a very simple experiment, and you give certain bandwidth, right? For instance, if you do a heralded down conversion, and then this photon will have certain bandwidth, and it's going to give you interference pattern, and from that you can actually measure the coherence length. From that you can calculate the bandwidth. And let's say you detected these photons here. Now, if you do a different detection. So I mean, you can put your detector here, or you can put your detector here, right? I mean, it's a single photon detection. So the options that you have is whether you put the detector here or whether you put the detector here. And you get exactly the same output, except that obviously the fine oscillation, it will be different. I mean, there will be a difference in phase, but you don't really care about that. All you care is the width of these interference fringes, and they will be the same. And if you do an experiment, I mean, you can find that they are the same. So in the case of single photon interference, whether you detect, these are the only options that you can do. So they give you the same coherence time. So you may consider this as a sort of a unique value to a particular single photon. What about, so basically the detection scheme does not affect the coherence time in this case. But what about when you do a two-photon interference experiment? In this case, you have a bit more diverse option of detecting these pair photons. I mean, you can detect 2 photons here and 0 photons here. You can detect 1 photon here and 1 photon here. And in the case of a quantum interference, I mean, this detection, they give you sort of a very different interferometric signals. One gives you a dip, the other one gives you a peak. So if you do a 2-0 detection, you have a peak, and you can actually try to measure the width of this one. And if you do a 1-1 detection, you also have a dip, and then you can try to measure the width of this dip. And you can try to compare whether these two are the same. And you can try to now generalize this, having n over 2 photons here, n over 2 photons here, and then you can combine this and the beam splitter, and then you will have many different possibilities of detection, right? And then all these detection possibilities. And some may give you sort of like a peak of this type, the others may give you a dip, and there may be some others. And then you measure this, and then you try to see whether different the peaks that you measure, they are whether identically the same. So actually we have done these calculations and then this measurement for a number of different cases. So basically, what we are asking is that depending on how you set up your measurement, does the coherence time really define, or really depends on how you do it? So the setups are very similar. So the multi-photon detection is basically the same. It's basically fiber cascaded detectors. So if you do a biphoton experiment, having 1 photon here and 1 photon here, you only have really 2 options, right? I mean, having to detect 2 photons here and 0, which we call 2-0 detection, and then you also have then 1-1 detection. So to be able to measure this width very carefully, we do this detection for a very long time. So for each data point, it's accumulated, what, 14,000 seconds. The other one is slightly less, but you see that we then fit this data to a Gaussian, and they fit very nicely. And these 2 values within this measurement error, they are pretty much identical. And we can actually calculate that these 2 must be identical. So for the 2-photon case, these coherence times are sort of uniquely defined, and this coherence time that you see is actually identical to the single-photon coherence time if you do an experiment, or Mach-Zehnder interference experiment, by just taking single photons and do the interference experiment. But what happens if you do a 4-photon experiment? Then you have a sort of more diverse options, right? I mean, you can try to detect sort of a different combinations of your detection firing schemes. So if you do, let's say, 4-0 detections, so all the photons are sort of going to this detector and the output of this beam splitter. Then you have a peak that you see. And this peak, if you do a Gaussian fit, it looks like that. So this number is slightly now different than the previous case. But if you do a different detection, so you detect 3 photons here, and then you detect 1 photon here. And instead of a peak, now we have a dip. But this dip doesn't actually go all the way down to 0. And we can actually calculate this, and then this actually doesn't go all the way down to 0. And then these 2 values are actually quite different. It's significantly different. And so basically, when you have 4 photons, right, depending on how you do it, you have a different peak or dip, but then this peak or dip, they actually give you a different width. So you're sort of wondering which one you need to use when you define multi-photon coherence time. Well, what about when you do go with n photons? If if you have n photons, right? I mean, what really happens? So now you feed, so here there's n over 2 photons, and then n over 2 photons, and then they are overlapped at the beam splitter, and then there will be really widely varying possibilities of measurement. And obviously, experiment is going to be quite challenging. So we resort on calculation. So when you have 6 photons, having 3 photons here and 3 photons here, and if you do a sync 0 detection, so you detect all 6 photons here and 0 here, and then you have a peak, and then this peak obviously will have a certain width. And then if you have a 3 and 3 detector, so if you detect 3 photons here and 3 photons here, then you have a dip, and it turns out in this case the dip actually goes down all the way to 0. And then these two plots actually they give you a different number in terms of width. If you go to 8 photons, you can do 8 0 detection, give you a nice peak, and then the kind of dip that you have is actually different. I mean, in this case, you have sort of symmetrically arranged detectors, but in this case, it's 5 photons here and 3 photons here, and this gives you sort of a dip here, which goes down all the way to 0, but this dip actually is much broader than the peak that you have. And if you go to 10 photons, the changes become a little bit bigger, and if you go to 12 photons, the changes are actually even more dramatic. And it will be very interesting to be able to do this experiment, obviously, but it's going to be quite challenging if you want to do this using Doppler. So let's try to quantify this. So you have certain width of your interference, let's say, fringes, and depending on your measurement schemes, and then you normalize that to 2 photon interference case. So basically, you have certain width that you measure here, then you normalize that to the case of having 1 photon and 1 photon here, and then detecting 1 photon here and here. So basically, the case of momentum. And if you normalize that, so in this horizontal axis, you have the photon number, and vertical axis is this normalization factor. And depending on how the measurement detectors are arranged, so in this case, you detect 1 more photon here, and so basically 2 more photons here, and less photons here and more photons here. And as you increase the number of photons, the width basically gets increased. If you do a symmetric detection, you actually get a different value. And if you do even more sort of an asymmetric detection, you sort of have a different case here as well. And then if you do, if you detect all the photons in one output, for instance, all the photons here, and then this, you actually get a dip. Actually, you get a peak, but this width of the peak actually gets decreased. So you have, and if you try to fit it, this actually fit goes down to 2 over square root of n. We don't know what actually that means. This may mean nothing, because what's 2 there? So
you know, you're fitting these all the Gaussians, but Matt just said a lot of them don't look like Gaussians.
Yeah, we are not actually fitting. So these are not the fits. So these are calculations, assuming you have a Gaussian spectrum.
What's the width of the blue one in this case? Is it still full width at half maximum or something?
Yeah, we are measuring the full width at half maximum.
Okay. But that might not be a good thing to do.
But you have to have some measure, right? Full width half maximum is a good measure of things.
If it's a Gaussian.
But then how do you measure? That's also a question, right?
All right.
So basically, you have sort of one case that's uniquely defined. Just 2 photons coming into a beam splitter, and that's the only case where you actually have, I mean, that's how, because it's really normalized. But all the other cases are really measurement dependent. I mean, depending on how you arrange your detectors, they become different. So I guess I've used up my time, so just, it's not really of a summary, but sort of a restatement of things that I've already said. So I would like to say that multi-photon interferometry is a, I mean, it's a good system to study quantum coherence in photonic systems. Although you can do quantum computing and then all the other things, but still, without using very fancy equipment, you can do some things. This multi-photon interferometry has revealed that when you go from quantum to classical, there's sort of a non-monotonic feature in transition. And also the coherence times that you define, as you said, fully maximum, it's really measurement dependent. So there are some applications in quantum metrology. Frankly, I do not know. I hope that there is something, but at this point, we do not know. So let me just show the reference, and then I'll stop. Thank you very much.
Thanks, Yoon. Some very elegant results. Do we have any questions about it? Yep. So, well, great work. I love the PNAS, and I think I'll have to study more on the second one. So I'm a bit confused. So the quantum coherence, usually when I take an Mendel dip, I actually say, well, I fit it and say the coherence length of my photons is actually the fit, exactly the same thing. And that's also, I think of it as a real photon length. So I say my photon is this one. So I kind of mix a quantum and classical, saying the same thing. Are you saying that when you go to higher photon, that's not the same thing, or there is still like a real photon? I think the photon has a length or a coherence time that is defined, and then we see this interference pattern length or time changing because of, I don't quite understand what is.
So I guess typically, I mean, you define your bandwidth, right? And then from the bandwidth, you calculate what the coherence time is going, coherence length is going to be, and that's how you see in the measurement when you do interferometry. But quantum interferometries are sort of more complex, right? You actually have you involve more amplitude, so the measurement itself is not unique in some sense. You can do different measurements. And different measurement actually reveals different interference signatures, and they can all have different, let's say, fully that maximum.
Yeah, but is there an intuitive way of explaining why the width changes?
Intuitively, I don't know if I can do it intuitively, but I personally see it as so even coherence time is really how you project it. And that's sort of a
I would like to understand the theory, but I can't. Thanks.
We've got time for one more quick question.
I guess in a similar vein, I mean, I kind of see it the other way around. That the pulse coming in has a complex amplitude and the multimode frequency basis.
Yeah.
And I think of that thing as being the one true expression of my photon, and the measurement is then, all the measurements are various ways of getting a bit of information about that.
But your measurement must agree, right?
Pardon?
So which measurement do you know is the unique one?
Oh, no, you're absolutely right. But I think if I make all of them, then I can think, well, I don't think I've got a Gaussian to begin with. There's some unknown spectral function f.
Oh, actually, in this case,
and let's suppose I can use those 10 pieces of information to now start to reverse engineer some information about what the true pulse spectrum was.
So to make sure that actually it doesn't happen in our case, actually we filter this. So I think it's 3 nanometer spectral filters that we'll use, so sort of to restrict the photon bandwidth to a particular form.
Right, but you can turn it the other way. You could have someone give you a pulse which you don't know what it is, and now you can reconstruct it to 10 bits of information. Because every measurement is giving you a different handle on the internal structure of the spectrum.
Right. But from that, what do we conclude?
You'd say you build a model for the pulse which has 5 numbers corresponding to its intensity shape and another 5 numbers corresponding to the coherence.
How many photons are coming in?
Yeah, but they've all got the same spectral multimode expansion. So you could use these measurements to unravel what that is.
Yeah, in this case, for instance, in the measurement, right? I mean, we are doing 4 photon detection, and the higher components are very big, and we actually make sure that. And in the calculations, we are actually limiting particular Fox states. We are limiting Fox states. So this calculation is a Fox state calculation. So we don't actually have contributions for other Fox state terms. So we cannot really go expand this term coming from, let's say, higher photon number. I mean,
Okay.
Okay, I think we're about to break for tea, so can we thank both of the speakers in a session again?